cost of retrofitting as a function of the geometry. The equation that we see here is, but I do also have ratio of the retrofitting. We observe here that as long as we the seismic performance, until reaching an optimal beyond which the life cycle cost is not going to decrease, instead it's going to increase. Now, let's look at this figure, which compares at different levels of capacity demand ratio for all the strategies. And what we saw here is that RC jacketing is the dominant. It's better than the other two strategies at all capacity demand ratio level. So in this case, if your target is just to optimize life cycle cost, then RC jacketing is the best choice. Now, what's going to happen if I add indirect losses into the equation of life cycle cost? And I'd like to highlight here that the indirect losses are basically the cost of relocating building occupants to temporary housing facilities during the time that the building cannot be occupied. So here we see a plot of the overall life cycle cost versus again, there is not much of a difference here. The trend is the same, the optimal points are the same. But once I look at this figure, which compares the in life cycle cost at different capacity demand ratio levels, it turned out that the FRP and steel jacketing are actually better at capacity demand ratios less than 90%. And RC jacketing is better at the remaining levels. This means that indirect losses can actually change my mind about the choice of the best retrofitting strategy. What's going to happen if I consider a lower hazard level? So instead of L'Aquila, let's look at Firenze, which has a very low seismic hazard. In this figure, we see the variation of the life cycle cost for the FRP, but without considering indirect losses. And it turned out that the retrofitting is not feasible because the life cycle cost is not reducing. On the other hand, if I consider the life cycle cost with the indirect losses, I can achieve more than 20% reduction in life cycle cost, which means that indirect losses can actually change my mind about the feasibility of seismic retrofitting. Moving now to sustainability and life cycle carbon, it can be treated exactly like the cost. It's basically the retrofitting of carbon plus the carbon of retrofitting, sorry, plus the carbon of repairing seismic damage. It's exactly the same concept. Instead of euros, we have now carbon emissions. I also fitted equations that express three strategies as a function of the retrofitting geometry. And in these figures, again, we observe the variation of the life cycle carbon, and the trend is the same, and the optimal points are also the same. However, when we compare the three retrofitting strategies in terms of reducing the life cycle carbon, we could see that the FRP and steel jacketing are actually significantly better when I compare them to RC jacketing, but this is for capacity demand ratio less than 90%. On the other hand, RC jacketing would be better for capacity demand ratio which is larger than 90%. So the main insight here is that sustainability can actually alter my decision-making process, even though there is a high correlation between the embodied carbon of damage. There's another way to integrate the carbon emissions cycle cost, which is by converting the emissions into money. And the concept of carbon tax, which is a tax imposed by the government for each ton of carbon emissions, which means that my total life cycle will be the original value plus the carbon emissions multiplied by the carbon taxes. Within the borders of Europe, it could be as low as 2 euros, and this is like Estonia, and it could be as high as 120 euros per ton, as in Switzerland. Right now, there is no tax going to use Switzerland for illustration purposes. And on the left side, we see the variation of the life cycle cost without any carbon tax at all. And on the right side, I see the variation of the life cycle cost with the carbon tax. What we can observe here is that carbon taxes are just causing a slight vertical shift in the life cycle cost, but the trend is the same, the optimal point are the same, and there is no influence or whatsoever on the decision-making process. And the final point is about the optimization of seismic retrofitting. I highlighted the simplified fragility-oriented approach in the first part, which relies on the linear relationship between fragility and capacity demand ratio. Now that we have the consequence models, we can even expand that into loss or cost instead of damage. And here, for instance, I fitted a very simplified relationship that expresses the seismic loss as a function of capacity demand ratio. And in that case, I just start the design process by specifying the desired level of loss and getting the target capacity demand ratio that I have to use, I have to achieve during the design process to get the desired loss reduction. We can even go a bit further by optimizing the entire life cycle cost. And in this case, we have the simplified fragility-oriented approach, we have consequence models, and we have equations that estimate the cost of seismic retrofitting. So, final key takeaway, we saw that the indirect losses can actually influence the retrofitting selection and feasibility. And in terms of sustainability, if we think that the emissions are an essential part of the decision criteria, then it's true that it can alter our choice of the best retrofitting strategy. However, we have to take it in the form of life cycle cost and not only in terms of seismic damage. However, if we are interested in money only, then there is no point of wasting our time in computing the carbon emissions, converting them to money using carbon tax, because the decision is not going to be affected, nothing will change. It's just going to offer us, let's say, a better estimation of the life cycle cost. Unless one day the carbon taxes become so expensive, like 1,000, then we might have another say in this process. There is an extra part of my thesis. I'm not going to discuss it now because I think I'm running out of time. It's about the effects of sequences of ground motion on the fragility and vulnerability of RC frames. It connects somehow with the retrofitting decision criteria, but of course we can discuss about details later. For now, that's all for today. Thank you very much for listening, and if you have any questions, please do let me know.
Thank you, Karim, for going only slightly above 25 minutes. We can now open the discussion with members of the evaluation committee. See, yes, it works, Flavia. We can hear it.
Fantastic. Thanks for the presentation, Karim. Amazing and interesting work. I have one question about the way you calculated the CO2 emissions. Mm-hmm. So at the moment, you assess the CO2 emission based on the materials, mm-hmm. basically on the quantity of materials. Mm-hmm. And indeed, this is a nice way to do it, independent of the location mm-hmm. and of other factors. If you had the opportunity to introduce other factors that can affect CO2 emission related to retrofitting, let's say transport of material and so on, do you think that, first of all, do we have available data to assess this? And in case for specific case study we have available data, do you think that the main conclusion you have come up would change?
Yeah, thanks a lot for this question. Actually, it's very important, and I didn't clarify this part because it needs a bit of explanation. So the thing is that if you look at this figure, which I didn't introduce in my slides before, this shows you all the stages of life cycle of material. The part that I focused on was, as you said, Flavia, the material production, which is A1 and 2 and 3. These basically, if we forget about the use stage, because this should be similar when we compare between retrofitting strategy, this A1 and A2 and 3 represent at least half of the life cycle cost, and it could be even more. Now, you mentioned something very interesting, which is the effect of other factors like transportation. Yes, it's important, but you know, when we refer to the data of embodied carbon, most of the manufacturers are just considering the A1 and A2 and N3 because it's the most significant part. Think of transport, we can include it. There are simplified factors that depend on the type of the vans that carry the materials. You can multiply it by an estimated distance that the truck can carry within the site and the factory. If it's going to introduce an addition into the life cycle cost, it's going to be within 4 to 5%. But because of its high uncertainty, we haven't looked at it. But it could be, like, in my opinion, part of the future development to include these factors.
Thank you very much. If I have time, I would like to ask also a second question. In the first part of your presentation, you emphasized how important it is to have regional models, for example, for the FEMA, to implement the FEMA P58 framework. Do you envisage a future in which we will have a regionalized CO2 model? So at the moment, you have a non-site specific sustainability assessment because you are assessing everything based on material. In a model that can include other factors, do you envisage the possibility of assessing, of having a regional-based sustainability model?
Yeah, indeed. And actually, this is the reason why I was talking specifically about this part. Oh, the slide has disappeared. Let me just go to the particular slide that talks about that. Okay, so looking at this figure, I was thinking, I derived consequence models of embodied carbon for Italian building components, but does that represent the entire Italy? Of course not. I also did it at the building level, so we have damage to carbon ratios, but these are for 9 case study frames. I know that they represent a large portion of buildings, but still